Everyone, I hope that you're having a great day so far. In today's lesson, we're going to learn about something called relative motion. And specifically, we're going to be looking at adding a lot of velocity vectors together. This is the topic that the mathy physicsy part of it is not actually that hard. We're just adding two vectors together to get a third and trying to figure out what that third vector is. It's something we've done before. But this can be pretty tricky in terms of the language that questions will use. So I think the thing you'll have the most trouble with is like pulling apart what words mean what and piecing that all together. It can often be really difficult to understand what a question is asking. So let's kind of jump in on that. Before though, we talk about velocity vectors and relative motion in terms of like the academic sense and what we've got in a node and example problems. I just want to look at some of the examples we see from this in the real world that I think will help give you a better understanding of what we're talking about here. Okay, so if any of you have been to Billy Bishop Airport, which is on the island in Toronto, you will have experienced, if you walked through the tunnel and didn't take the ferry, these moving sidewalks. We see these in airports a lot, but also in other places as well, where you got to move a lot of people quickly. And so this is the moving sidewalk in Billy Bishop Airport that I decided to walk on, and I'm going to show you what happens. I found a time when there wasn't anybody there, and I was able to walk backwards. So here I go walking against the motion, and I want you to kind of pay attention to what we're seeing in terms of what's happening. So you can see that that I'm walking. I'm going at some velocity, right? I'm going to the right at a certain velocity, and I'm walking. Um, but I don't actually appear to be moving anywhere. I'm actually physically, my body is staying in place, even though I have a velocity to the right. And you can very quickly understand that's because the moving sidewalk is moving to the left. So what I've done is I've added two velocity vectors here. I've added me moving to the right at I don't know 1.8 meters per second, and I've added the sidewalk moving to the left at 1.8 meters per second. We've added two velocity vectors together, and because they are equal and opposite, they add to zero. And so my actual velocity when we look at it is zero. I'm not moving at all. And we call that my ground velocity because relative to the normal ground that's not moving, my velocity is zero. However, relative to the sidewalk, I am moving at a certain velocity. So now let's look at a different example. Previous one, we added two velocity vectors together and they worked out to be zero. I wasn't actually moving. Let's have a look at when I change direction here. So there you saw me go zooming by. And what we're doing there again is we're adding velocity vectors. The sidewalk is moving to the left. I am also moving to the left. We add these two velocity vectors together and we get my resultant velocity. And we compare my velocity to the ground. Now, compared to the escalator, I'm just moving at my regular walking speed, maybe 1.8 meters per second. But compared to the ground, I'm actually moving at double that, right? Because I have both my velocity and the moving sidewalk velocities added together. Okay, now what happens if we have a different situation where maybe there is a car on a treadmill? So I got my son to help me with this one. Here's this little motion car that you can turn on, and we managed to get the treadmill to go at the same speed as the motion car. And now, what if the motion car? What if the treadmill is a little faster? We can see that when we add those vectors together, it pushes them to the right. Now, what if we point both of those vectors in the same direction? Now, instead of canceling each other out, they are in fact adding together to make one bigger velocity. So it is actually a really normal thing that we experience in everyday life is adding a couple velocity vectors together and seeing what their result is. The mediums we had there were a moving sidewalk and a treadmill, right? That's our moving medium, our thing that's moving. So the ground we consider stationary, and that thing is moving, and that thing affects our movement. But this is also true of planes in the air and boats in the water. This often comes up with like motion of everyday objects when they're moving in the mediums that we have on the earth, like air and water, and they're affected in the same sort of way. You can probably it makes sense that if you're in a river and your boat is moving with the current, you move faster. If your boat is moving against the current, you'll move slower, and you might be able to hit just the right speed that you actually seem to stay in place relative to the ground around you. You're not moving at all. Um, this is also true of dogs in rivers. So this is my dog Gus. I'm going to have him start doing some stuff, and then I'll talk you through what we're seeing here. So here goes Gus. I threw the stick for him. He's swimming against the current. The current is pushing back on him. Now his velocity, we would call this his heading, is a little bit higher in magnitude than the current. So he is able to continue to move forward against the current. When he's swimming with the current, he's much faster. Now we're going to go at a bit of an angle here, and Gus is going to get hit on his side with the current, and he's actually going to move diagonally. He's trying to swim mostly upstream, but the current is pushing him to a degree sideways, and he's getting pushed sideways down the river. So I like to call this dog physics, right? I like to work in physics any way I can. Now, there's a great simulator that I'll want you to play with, but it can really help bring to light what we're talking about here. So this is one of the ones you're going to want to try out to check it out and see how it works. So let me get onto the simulator here. There we are. Okay, and what I'm going to do is I'm going to send this boat across the river. Now I notice up here in the upper right-hand side, velocity of the river relative to the Earth is 3 meters per second. So that's how fast the river is moving. If I turn on my vectors, I can see the river velocity there moving to the right. The velocity of the boat relative to the river is 4 meters per second, and it's headed straight north. So if I let it run, of course, it's going to move downstream a certain amount, right? Now I could instead reset that and turn my boat upstream a little bit to try and fight the current. And in fact, boats that want to go across the river, directly across, will do this. And you'll see a video later of about doing this. Now I didn't quite make it. Now, if I want to make it across the river, I can turn on my vector diagram, and now I can actually turn things just enough. Now, normally if I'm going straight across, this is the situation I'm dealing with. And when I'm adding vectors, I have the vector that's to the north. That's the heading of my boat. That's my boat motion relative to the water. And then I have a vector that's directly east. That's the current of the river. The river relative to the earth or relative to the ground. So you can see the little subscripts there, B to R, boat relative to river, R to E, river relative to earth. And then my resultant vector, where my boat is actually going to move, is the velocity of my boat relative to the earth. How does my boat move relative to the shore? We can see that's going to move off to the right, and we can see the boat follows that vector at an angle. But let's turn my boat a little bit. Let's say I want to get right across the river. I can turn this enough such that my resultant velocity of my boat relative to the earth is straight across the river. Basically, the x component of my boat's heading is canceling out the river current. And there we go. I'm going to actually go into the current, and that'll allow me to move straight across the river. Now, an important thing when you're working on these problems that you're going to need to remember is, in order to get across the river, the only thing that matters is the heading of my boat, or we call this velocity of my boat relative to the river. Okay, the current of the river doesn't actually matter, and I can show you that's true, right? Because say I'm headed straight across the river here. Let's let it run and see how long it takes to get across at 4 meters per second. I see it's a time of almost 13 seconds. Okay, let's reset it and turn our river velocity to 0 and run it again. And we see it's the exact same thing, almost 13 seconds to get across the river. So it actually doesn't matter what the current is, because the current doesn't move me across the river at all. All that matters is the boat, right? Now, if I turn the direction of my boat a little bit, now the heading of my boat, the velocity of my boat relative to the river, I don't have as much of a component of that that's headed straight across the river, right? If I go completely to the left, now there's no component. I'll never get across the river. If I go completely to the right, there's no component perpendicular to river. There's none of it that's pointing across. If I go at a 45-degree angle, let's say, something like that, that's pretty close. There we go. Now I have a component that's pointed across the river. And as I go, oh, I forgot to turn my current back on. Hold on. Let's reset that. And let's turn my river back to 3. There we go. We'll run it. We'll see that it's going to take me longer to get across the river because not as much of my boat's velocity was pointed across the river. Some of it was pointed upriver, right? Some of it was pointed upriver. Okay. Um, so when we're describing directions in these situations, especially with river boat problems, we'll often describe it relative to the shore. And we'll say upstream 45 degrees relative to the shore, right? So if I reset it and I'm like this, I'm saying my boat is pointed upstream 45 degrees relative to the shore, or I could go say downstream. If I go to 10 degrees here, downstream, that would be 80 degrees relative to the shore downstream. So we can describe directions in relation to the physical environment. But the key idea is we're still adding two vectors together and we're seeing what happens. Now, let's go back to our lesson. And let's talk about this like a little more academically. Okay, so velocity is a vector. We know that velocities can be added like any other vector. Me moving on an airport sidewalk, we add the two velocities together and they sum to zero. Right? And I'm drawing my velocity vectors there. Now we could have three possibilities. We can have one-dimensional that's linear, two-dimensional at a right angle, math is a little easier, or two-dimensional at a non-right angle, in which case we got to use vector components, right? We're very familiar with that. Okay, let's have a look at our next page here. A few tips about relative motion. The motion of an object can be described differently by two different observers. You're going to see that in the videos today, and those will help make it clear. Someone sitting on a boat and seeing a dog walk past them sees that dog moving at a different velocity than someone who's sitting on shore and seeing that dog walk on the boat because we're adding velocity vectors together. So we call those different frames of reference, and a reference frame is just a position from which you're describing the motion of the other stuff you see around you. Analyzing the motion of one object relative to a specific reference frame, we call that relative motion. That's the name of our lesson. And this comes up in, you can do this with like spaceships and speed of light. This has all these applications for like some pretty gnarly special relativity Einsteinian physics that we'll get into later in the year. And so we call the object's velocity relative to a specific reference frame. That's called its relative velocity. We're going to analyze some specific situations with moving mediums. These are great places to start. So airplanes in the wind, boats moving in a current, right? It's often convenient to use components in these situations, right, in order to analyze the motion of an object, because perpendicular vectors are mutually independent. So that means that the time it takes for a boat to cross the river doesn't depend on the speed of the current, because the current is not in that direction at all. Only the component of the boat's velocity matters, and I showed you that with the simulation. Okay, let's talk a little bit here about our formula for this. We know when we're adding vectors, we just add them together, right? You just take your two vectors and you just add them together. That's pretty easy. And that's all this formula says. It says if you want to get the ground velocity, that is the velocity of your object relative to what we consider the stationary ground, even though we know the Earth is moving and the galaxy is moving, blah, blah, blah. But we consider the Earth stationary for our frame of reference. Our heading is where our object is trying to go, kind of where the boat or plane is pointed, but not actually where it goes. Think about that boat in the simulation. It might be pointed a little bit upstream, but when you add the vectors together, it's actually moving a little bit downstream because it doesn't beat the current. So heading is where our thing is pointed. Our medium velocity, medium is the stuff it's moving in, so that would be the current of the river. Okay. Now, I've also written these out. Your textbook is going to use them with a V for velocity with a little subscript on it. Okay. You'll notice in one of the videos, I just write GV for ground velocity, H for heading, and MV for medium velocity. You can do that too. I'm just trying to follow what your textbook does a little more here so that we can make those make sense together. Now, here's the thing. I could say if I wanted to find my ground velocity, right, as this formula, right, I can just take my heading and my medium velocity, and I can add those together. But what if I want to find the medium velocity? What if I want to find how fast the river is flowing, for example? Well, here's what I can do. Let's do a little algebra and move these around. I can subtract the heading velocity from both sides. So subtract this one from both sides. So it disappears from the right, appears over here on the left. I'm just going to do some algebra and rearrange that. Oh, sorry about that. Ground velocity minus my heading velocity equals my medium velocity. Okay, so I've rearranged this equation, right? Here's the catch. The ground velocity doesn't change. The heading, though, you'll notice is being subtracted. What do we do when we subtract a vector? We turn it around and change it to positive, right? Turn it 180 degrees, change the direction, flip it around, and make it positive. So that's what I'm going to have to do before I try and add these together. Since I'm subtracting that vector, I want to turn it positive. I'm going to have to write the vector in and then change the direction by 180 degrees and change the sign to positive, and then I can continue as normal, and I can add these two vectors together by drawing a cute little vector diagram or using vector components or all the stuff I was looking at last week. So beware of those. Depends on what you're looking for. If you're looking for your ground velocity, easy, you just add these two together. You may be in a situation where it is one-dimensional or more likely a triangle at 90 degrees, and you have to figure out your resultant velocity, or it could be vectors working at weird angles, in which case you have to use your vector components, your x's and your y's. And then you have to add your two x components together like that. And your y components, one goes up and one goes down like that. So this would be your resultant, right? Using vector components. And then we do Pythagorean theorem tan ratio, just like we did last week. In our second case, right, if we're trying to find the medium velocity, we got to turn that second vector around to make it positive, and then we can follow the same steps. So hopefully that stuff you've been doing last week, now we can apply it to these sorts of problems. Okay, let's just wrap our brains around the language a little bit, because this is the part that most students find they have trouble with. It is a bit tricky, so I'm going to try and give you some of the language that you're going to see in these problems and in your textbook. So first of all, I like to call it ground velocity because I find that makes it easy for me to understand. That's the velocity of an object relative to the unmoving ground. You will see this one in your textbook, but sometimes it goes by other names. This is often called velocity of the object relative to the Earth, and it would be denoted by VOE, or it could be V. Let me write this in. Could also be V P for plane, E for Earth, or B for boat, E for Earth. It's the velocity of the object relative to the Earth. Okay. So your textbook will usually use like PE or BE when it's solving them. So here's some examples. Regarding moving sidewalk, Mr. Roy's ground velocity is 0. He's not moving relative to the ground. That would be the first one we saw. Another example that you might see in your textbook or in questions: determine the velocity of the plane relative to the ground, VPE. Or a pilot is flying to a destination 220 kilometers north of her present position. That would be our that would be our displacement, right? And if we also have the time, we can figure out our ground velocity. That's the direction the plane actually needs to go, not the direction it's pointing, but the direction it actually needs to go because it needs to get 220 kilometers north. Okay, so those would all implicate ground velocity. If we're talking about something called heading, heading is the velocity an object would have if nothing else affected it, right? So when I turned off the current in that simulation, wherever direction I pointed my boat, that's called my heading. So it's where your plane or your boat is pointing, but not the direction that it actually goes necessarily. Because if there's a medium moving it too, we need to add those vectors together to see where the object actually goes. So caution with this. You will see your textbook use the word heading, but it also uses some other language. This is often called the velocity of the object relative to the medium. So the velocity of the plane relative to the wind, or the velocity of the boat relative to the water. So you might see VBW for velocity of boat relative to water, or velocity of plane relative to air for VPA. So whenever you see in a question something denoted as the velocity of the object relative to the medium that it's moving in, it's talking about the heading. Your book might say the heading of the motorboat is 13.4 meters per second north. It might say the airplane has an air velocity of 200 meters per second west. You'll see this one in your textbook as well. Air velocity would mean its velocity relative to the air. Could say a helicopter travels at 62 meters per second north relative to the air. These would all indicate heading. I find personally this is the hardest one to decode from a question. When you're looking at a question to figure out which one is the heading, I find it the most difficult. Last one is our medium velocity. I usually find this one pretty easy to pick up on. It's the velocity of a moving medium which affects the motion of an object. So it's often called the velocity of the medium, like water or wind, relative to the earth. That means if I'm standing on the earth, the still ground, and I look down at that river or I look up at that wind, what direction are they going relative to a stationary observer on earth? We might call it VAE for velocity of the velocity of the air relative to the earth, or VWE, the velocity of the wind relative to the earth. Okay. Um, Examples: the moving sidewalk has a velocity of 1.2 meters per second backwards. So the sidewalk is the medium in this case. The wind blows at 21.5 kilometers per hour south 34 degrees west, affecting a flying plane. It could describe it in like casual terms like that. We're talking about the wind relative to the ground. Or a river has a steady current of 0.5 meters per second east. Those are examples I've grabbed from your textbook that would relate to this. Okay. So the hope is that this helps to give you an understanding of decoding these questions. I find that's the hardest thing going forward. Okay, this week, give these a try, jump in on them, see how they go. Remember, we have the textbook solutions when you're doing the check your understanding questions. Lean on those. Start by checking them early and often if you get stuck, and then try and move away from them and only check them after you've completed a question to try and see how you're doing. Of course, if you have specific questions or you're stuck on some of this, or you're seeking more clarity, send me a message and I'm happy to help out and give you some support in your learning on this. It is tricky. That's why I've put in lots of time so that you can try and practice these questions, but you need to do the practice to make sure you're feeling good about it. Okay, get out there and let's do some physics. Best of luck to you. Bye for now.